This conference will now be recorded.
All right. All right, so before I get started, any questions? Well, if anything comes up, please feel free to stop me at any point in time. So today we are going to start with the outside of the model onion I showed you last time. We're going to talk about model forcing. So before I start jumping into things, take a look at the picture that hopefully you all can see on your screen and tell me, what are you looking at? What's wrong here, and how do you think this happened?
Well, it looks like their snow fence trapped all the snow, and so they're taking snow measurements in an area that is deeper than what actually the snow is.
So all the snow piled up behind the snow fence here. Absolutely. Do you know why? Does anyone know why this fence is here? It wasn't designed to trap snow, I'll tell you that. It did that, but
Is that like an alter shield for precip gauge or something?
yeah. That's to slow down the wind for your precip gauge. So I think we got an idea of what we're looking at and how it happened. So what's a major problem if you're a snow modeler and this is your forcing data?
It's going to be wrong.
Yeah, in a really major way, right? So you got challenges at the get-go, right? Before you even turn on your model, you better be careful about. So we're going to talk about that today. So before you turn on the model, make sure you know what you're feeding it. So we've got, like last time, we're dividing today's lecture into 3 parts. Starting up with class logistics, we're going to talk a little about the homework, Pangeo, and Hydrashare. We'll then go through all the pieces of model forcing data, and then I'll conclude with giving you basically my opinions on best practices in selecting forcing data, particularly in complex terrain. So, all right. Just one aside, if anybody wants a textbook for this class, it's absolutely not required. You don't need it. I think this one is decent. It costs, I think, too much money on Amazon, but your library probably has it. So if you're looking for something that will talk about parts of a snow model for your own reference, this is one you might want to consider. Also, if anyone else has a favorite one, feel free to post on discussions. I really recommend this reference. All right, so where are we in our whirlwind month of snow modeling? So last Wednesday, we did our overview of the class and snow modeling in general. I told everybody to start reading 1 and write a research profile. I saw lots of good information on the discussion about people's backgrounds and research. Thank you. On Wednesday, the critique of reading 1 will be due. Are there any questions? Anyone have trouble finding reading 1 and the directions or anything? That's okay. All right. Today, even though you're supposed to working on the reading, I also want you to start working on homework 1, and I'm going to show you some. I'll show you some of the pieces for that today. Basically, it's not due until a week from Wednesday, but because this requires you to actually run the model and do things, I want you to turn it on and start pushing buttons so that you have plenty of time to ask questions because they're going to come up. So just start playing with it. So we'll be going over today meteorology, how to QC data and run a snow model. Homework 1 will be about changing the metadata that you put into your model and what it can do. On Wednesday, we'll be adding vegetation, what trees do to snow and how to model it. And we'll also, part of homework 1 will be metadata under trees versus in the open next to trees. How do you actually put that in your model? Great. So I noticed some of you sent me links to your Hydrashare account. So a few just directions. Hydrashare it's not required. You don't have to put things there for the class, but it's something CUAHSI provides that's a great service that I'm recommending you check out and use. things I want you to consider is that the Pangea, the cloud computing, will erase everything we put there within a year, if not sooner. So make sure you're copying somewhere. Your home computer is fine too, but Hydrashare is easy, and we're going to give you code to just port things over there. It's really designed to save things, but by the same token, CUAHSI has to pay for all the storage on there. So, please delete any test data output that you don't need. If you push something over and then you do another run that you think this is better, delete the one that's bad. Don't save everything. I know I'm personally bad with my own computer with that, but think about it's a shared resource of storage space. Also, you have the ability in Hydrashare to publish things. CUAHSI will issue a DOI. So if you're doing something on there with a collection of things for your research, you can publish it as a repository with your paper. However, please don't publish your homework. It's not because it's secret, you can make it open, but it's because CUAHSI actually has to pay every time they make a DOI for somebody. And if we all publish our homework and have DOIs, then we can put it in our CV, but not too many people will care, and CUAHSI will be sad they have to pay all the money. Also, once a repository is published, it can no longer be changed. So really, you want to publish it sort of when your paper is in final form, right? You're like, this is the model output I used in this paper to make these figures. This is my key findings. Anything you're still tweaking or playing with, don't click the publish data. Also, just want to highlight metadata details are beyond what I have time to cover in a month, but anytime you're saving anything, the more thoughtful metadata you can do, the happier you and other users of your data will be in the long term. So when you're uploading things to Hydrashare, you'll see in the directions we have like blah, blah, blah. But think about something actually useful that you put in there about your data, what you're doing. It's worthwhile. All right, so again, just logistics. Got the introductions on the discussion. Homework 1 is your week from Wednesday. Start now. Said that already. Make sure that before Wednesday you do, in addition, we're going to read slides, just log in, make sure you open the Homework 1 folder, which you should see in your work folder. You should have copied it as part of the introductory slides. And work through Homework 1A introduction and Homework 1B setup. I'm going to jump there in just a second. We will discuss Part C in class quite a bit, and Part D is most of your homework. So let me just show you what we've got here. Close this. So, if you're in the Canvas page, which I'm hoping you can see on my screen here, Homework 1 should provide you both with a link to a document that's about all the computing details and with a link to a document that gives you directions on what to do. I'm going to go into my, let's see if I can make everything larger. Let's see. Larger font. Better for people. Okay, so I can't fit anything. You should be able to see Homework 1, Homework 1A and B is what I want you to run through. Homework 1C, we're going to start talking about today, and we'll talk about more on Wednesday. Homework 1D is what you really have to do and modify. And then Homework 1E is optional. You'll be doing a class project. And we have things that are like, sort of if you're interested in the stuff here and want to keep going, these are some ideas to start you with other things you might investigate relating to this data set. In terms of running them, most of it is just, walking through, clicking the code, hitting shift return so you can run through the setup. If you will notice, if you start working with it and you walk away, it will shut down your whole virtual machine in the cloud, and you just need to start again. And you'll need to start, at the top of your library importing things in. Let me know as there are questions as you start working through this. I find it doesn't work really well for me to do live. It's better to troubleshoot. Also, if anybody needs a phone call or virtual office hours at any point because you're just feeling overwhelmed with this, let me know. I think most of things are designed to be self-explanatory, but that said, easy to get confusing. And any questions about this at this point? Just logistics, where things are? All right, let's jump into model forcing. Okay, so before you can run a model, you got to force the model with something. So, you know, where do you get forcing data? How good are they? And you might be thinking, wait, why is this all about meteorology? I really wanted to be a hydrologist. The reality is we got to be meteorologists too. You can't skip it. Okay, so, and this is just to show you from last week, forcings are, we're starting at the outside of our modeling onion. And we're going to get into the nitty gritty as we go forward here. All right, so hopefully this picture is something you've all seen some version of in some class before, right? We're thinking about snow. We need an idea of what are the fluxes of energy in our system. This is a paper from 1997 by Keel and Trenberth that appeared in the Bulletin of American Meteorological Society, where they're trying to quantify sort of on a global scale what are the relative amounts of all the different flux terms of energy coming in and out, right? So you can see that the sun is really, you know, driving most things. We've got incoming solar radiation. It might bounce off the clouds. It might be absorbed by the surface. It might reflect off our snow. We need to think about long wave radiation coming in from greenhouse gases and clouds in the atmosphere, long wave radiation being lost from the surface, going out to space. We need to think about sensible and latent heat fluxes and how much is absorbed by the surface. So these are the kinds of things we need some meteorology to put into our snow model. This is a slide put together by Mark Rowley, which you can imagine with the picture we looked at of that that precipitation gauge up in Alaska. You know, if your forcings are garbage and you put it into your, you know, award-winning model, your results are going to be garbage. Similarly, if you have wonderful forcings, you put them in a garbage model, you're going to get garbage. The other really fun thing about snow and hydrology is what you've probably heard is the equifinality hypothesis, is that sometimes you can be really lucky and have two wrongs make a right. And if both are garbage in just the right way, you will get answers that look exactly right. This is what you want to be really careful of. And then the one on the bottom is what we all strive for. All right, so here's an outline of what I'm going to go through here. So we're going to start with just at a point, okay? We're just going to be modeling snow at a point. What do we need to force the model, and how are these measured? And then, because your model is going to require continuous data all the time, what do you do if you're missing some data? And then what if you want to run a distributed model and distribute your data spatially? So you maybe have a good weather station at one spot that you need to extrapolate to other places. Then we're going to go through the more nuts and bolts. Okay, you got the data, but now how do you make a forcing file for this specific model? And then we're going to finish with, okay, one of the most common questions with snow modeling, I'm interested in some kind of climate sensitivity. What can I do with my data to run a climate experiment? And here we go. All right, so first one. So here's another great slide by Mark Rowley, he was my first graduate student, and he's, I think, the most graphically gifted. He makes the best graphics of anybody. All right, so here, this is the anatomy of an ideal mountain weather station. So here you probably have a tower somewhere in a nice clearing in the forest out on the snow. And what are you going to put on it? First, you're going to put a snow pillow, and we're going to color code things yellow if it's model forcing, and blue if it's primarily used for model evaluation, which we'll get to. So we've got our snow pillow. And why don't people call out what else are you going to put on your perfect met station here?
Temperature gauge.
Temperature, definitely. Let's see if we can get that next, or we get something else. Oh, we got a snow depth sensor. There we go. Here we got temperature gauge. What else do we want?
Relative humidity.
I heard relative humidity. Oh, we got a precip gauge next.
Wind gauge.
There's relative humidity. What else do we want?
Wind speed?
Wind speed, we got that. We got an anemometer with a wind vane.
Sorry. Okay.
Long wave, short wave radiation.
long wave, short wave radiation, right? Here's a Kippen-Zonin radiometer over here. It's got pyranometers, upward pointing, which will give us downwelling shortwave irradiance, and then a downward pointing, so this will give us reflected solar radiation, which could be used for model forcing to determine the albedo, or could be used for model evaluation.
Oil temperature?
What else?
Oil temperatures?
Oil temperature? Mm-hmm. So let me go through what else is on just this one, and then we'll see what else we get. We got pyranometers. Those are your long wave sensors. So you get incoming long wave and outgoing long wave radiation. We got our surface temperature, which will measure the surface temperature of the soil when the soil is there. It'll measure the surface temperature of the snow when it's not there. Not all snow models have varied soil temperature measurements, and it's not drawn here, but it's also a good idea to put in soil temperature and soil moisture measurements underneath. Anything else we're missing? Looks like a pretty nice weather station. So here's it in operation. So it's measuring snow depth, measuring snowfall. This is just because Mark is really good at PowerPoint. It's measuring direct shortwave radiation, reflected radiation, atmospheric and terrestrial long wave, upwelling long wave, which gives us an idea of the surface temperature and the emissivity of the snow. And here's a wind profile, which gives us an idea of the turbulent fluxes, which combined with the surface temperature and our temperature and relative humidity gives us an idea of the sensible and latent fluxes. So we'll be going through these in more detail as we go through. But to start with, this is what you want at the ideal weather station. This is to solve what we showed you basic equations last time. Here, du dt is the internal energy of your snowpack, is the sum of all the energy fluxes. So shortwave radiation, incoming minus outgoing, long wave radiation, in minus out. Precipitation, which depending on the temperature of the rain has some energy in it. Ground heat flux, that's what we want our soil temperature measurement. Turbulent fluxes, H is generally for sensible heat flux. P is for latent heat flux, and then the energy required to melt snow. So this is the basic equation we'll come back to again and again in trying to model snow melt. You can see a lot of it is really, atmospheric forcing. And you'll hear a lot of snow modelers say, if you give me perfect forcing, I can model snow perfectly. All right, so how good is this perfect weather station? So this is a slide, again, put together by Mark. And what he tried to say is, okay, well, first, what's the best we can do? If we go and look up all these instruments, what's the manufacturer specified accuracy? And basically, it says that you can measure precipitation to plus or minus 3%. Now, how many people raise your hand if you think we were doing that in the Arctic at all? How many people think we're doing that anywhere we're measuring snow? I don't see any raised hands at all. Yeah, so over here, if you go to the right, this is a higher uncertainty. This is from people actually trying to measure real things in the field and what they're reporting the actual uncertainty range is. So you can see a number of publications saying the actual ability to measure snowfall is plus or minus 75%. Precipitation gauges die in snow conditions quite a bit. You can also see that relative humidity sensors, are listed as being very good, but actually in practice can suffer from hysteresis, where they say it's moist much longer than it's actually moist. And you can be off by 25%. All right. So, given that uncertainty can be bad, any ideas? Anybody have any ideas of what should you do? I mean, I've got posted my favorite, always plot and check your data. Anyone else have favorite tips of what should we do to avoid putting garbage into our model?
Look at means and mins and max, make sure they make sense.
Yeah, that's excellent. You can do QC flat, right? If it's outside of some range, we're not going to use it. If the mean doesn't look sensible, we're not going to use it. Any other favorite tips?
Maybe just check your units.
Check your units. That is brilliant. Yes, always check your units. Make sure it makes sense. Also, a good check is converting the units that make sense to you, whatever you do. And I think somebody I think they really want us to see attendees.
Maybe also the context of where the station is, like if it's in a canyon or a ridge top, or kind of where it is located.
Yeah. Is it making sense from where it's located? Do you think it's located in a good location for what you're trying to use it from? So let's play a game called What's Wrong with This Picture? And I'm just gonna pick on some solar radiation sensors, pyranometers. So I'm gonna show you a picture and I want you to tell me what went wrong. All right, here's number one. This is a pyranometer at the Tuolumne Snow Pillow in Yosemite National Park, California. The blue lines are the observed incoming shortwave radiation, flux in watts per meter squared. The red line is the potential extraterrestrial radiation. This is what's at the top of the atmosphere before it gets attenuated by anything in the atmosphere at all. This is just by time of year and where we are latitude-wise that we could possibly get if there was no attenuation by the atmosphere. So what's wrong with this picture?
Something's up in 2009.
Yeah, what's going on in 2009?
It's too high.
Yeah, it's physically impossible, right? You can't get more radiation at your site than is possible from the sun reaching the top of the air. Right? Again, when we talk about setting some thresholds, something went really wrong with it in 2009. What's wrong in a couple days at other times? Then general looks okay. 2009 really wrong. I think Victoria's being. All right. So here's another shortwave sensor. And this is from Alptal, which is the Swiss station that's part of the SNOMIP2 Snow Modeling Intercomparison project. And this is incoming shortwave for water year 2003 to 2004. Again, I've plotted the observed in a red dashed line and the potential top of the atmosphere solar radiation in the blue. What do you see happening here?
Same thing from last time, this time on December 23rd.
So on December 23rd, it goes above. Something, what do you notice in the morning? What's going on in the morning?
I'm not sure.
So if you can, I don't know if you can see so well, is that the sort of first thing in the morning, you'll see that the observed shows sunrise happening before the potential top of the atmosphere shows it happening. So this doesn't necessarily mean that the sensor broke. What this one is something you need to be cognizant anytime you're trying to process observations and model output, particularly related to solar radiation, is that you actually need to be really careful about the timestamp. What time zone is it in? When is sunrise at this spot? One thing to know what model we'll be using is it calculates potential top of the atmosphere. And if you're feeding it observations that go beyond that, the whole model crashes. It stops going. It gets very grumpy. Where this can be problematic is that it's sometimes hard to find at met stations how they are actually measuring things versus putting timestamps on things. I know how many of you have ever programmed a Campbell data logger, and you have a choice. You can do an instantaneous measure. You can do an average measure centered in the middle of the hour. You can do an average measure over the prior hour. It's actually, if this is the check that's throwing your data out, it's important to figure out how things are working. And the other thing is the California Department of Water Resources converts everything to daylight savings time, but for a number of years they actually put daylight savings time in backwards. So instead of spring ahead and fall back, it sprang back and fell ahead. That took us a long time to find. The daylight savings time is problematic, and just knowing, sometimes everybody did everything right, but you just don't understand at what timestamp interval your data is being provided. And if you're running a check like this, you want to be sure you're checking the right thing, because this could just be, how things are being recorded. All right. All right. Okay. So now this is moving to Snoqualmie Pass, Washington, near my house. And what you see here is the blue is downwelling shortwave radiation, and the green is upwelling shortwave radiation. What's wrong with this picture?
Is that showing more is being reflected than is coming in some days?
Yep. Why do you think that is? Why would more radiation be reflected than is coming in?
Are they two different sensors?
I mean,
Is the upwelling separate from the downwelling?
The same time.
Does it have to do with cloudy days?
I'm going to show you guys a picture of my site at Snoqualmie Pass.
Obstructed trees?
What? There are trees there. The trees aren't to blame. So remember, a radiometer has a dome. One is pointed up, one's pointed down. It's recording how much solar radiation, how much light gets through there. So you can see in this case, we've got snow piled up.
Allow me to record.
I think it's yours. I think either you or Chris needs to not have audio, or you get feedback or something. Okay, thank you. So you can see that snow piles up on the top. There's no snow on the downward pointing sensors. Some of the light makes through the snow on the top, but not very much. So another check is if you're getting, more light reflected than coming in, you probably have snow on the dome. Radiometers are easy to go bad. We also had a heater. We were supposed to be melting off the snow. It just didn't work. For this, I also recommend putting out hunting cameras and just taking pictures of your radiometer every day, so you know when to throw out your data. All right, here, these are really fun sensors. So these are 3 locations, also in Yosemite National Park. And they're RAWS stations, so therefore RAWS are put out by the fire network. So they're out to measure fire danger. And these are just 3 locations, don't need to worry about too much. There's just 3 days in June in 2005. And what do you think's going on here?
The white wolf signal doesn't look symmetric, but the others do.
Yeah, it looks by far the worst. The other ones seem to have some issues too, right? So they're close enough that they should be getting the same amount of sunniness or not. So what might be happening at White Wolf?
Is there a tree or an obstruction to the west of it?
Yep, absolutely. Yeah. So if you're not careful to put your pyranometer up higher than all of your trees, it can get shaded at the same time every day. That can mess up your snow model quite a bit if you're not careful. This is a particular problem in a national park because the rules are such that you are required to hide all your met stations. So it's really good to hide them behind trees, but then trees shade your radiometer, so you'd better come up with a way to compensate for that. All right, so we QC'd our data, and clearly we threw out some of it, right? So you're very likely, even if you thought you had a lot of metadata, to find out that you are missing some of your data. So let's go through some best practices of what you can do to make up some data. This is from Mark. who states that the ideal snow station is elusive. Looking at 1,318 weather stations, this is most of the SNOTEL network, plus a few more that measure snow in the western US. You can see we do pretty well at ones that measure temperature and precipitation, but as soon as you want anything else, there's really only one or two that actually measure shortwave radiation in all of the western US at over 1,000 stations. So you are highly likely to need to make up some metadata. Radiation is the least measured parameter. And the majority of MET stations just have two observations. They have just temperature and precipitation. So you have basically, here they are. You can also see where the sites are. I think the Boise contingency has a lot in Reynolds Creek out here. Snoqualmie Pass, that's for the Washington contingency. There's some good sites in California and some good sites in Colorado. But in general, you're going to have a couple of scenarios, right? You know what your model needs, and here's what you typically have. So you either have case one, you have no data whatsoever, or you have case two, where you have just your a snow depth sensor, a precip gauge, and a temperature sensor, and you need to invent all the rest. So any ideas? What should we do?
Use model data such as WRF.
Yeah. Absolutely. We could take output from an atmospheric model. What else could we do?
There's equations for trying to derive radiation based on temperature.
Yeah, absolutely. There's a whole bunch of empirical methods. If I have measurements of a few things, how do I invent all my measurements of everything else? Or not invent, estimate, right? Yeah, so we use empirical methods. So for example, as I think Connor was saying, you take the daily temperature range, right, Tmax minus Tmin, and we know that on a sunny day, that's a much greater range than on a cloudy day. And so from that, we get an estimate of whether it was a sunny or cloudy day. That gives us an estimate of the atmospheric transmissivity. And from that, we can get an estimate of the incoming shortwave radiation. We could also use spatial interpolation if we have a good MET station somewhere nearby. We could use a weather model, or we could use satellite data. And as part of homework one, you're going to look at some empirical methods for estimating the long wave and see how much of a difference they make in your snow modeling based on which method you choose. So just to walk through, this is mostly so you have a reference going forward. So one thing for air temperature, you'll often find that there's a lot of data from like cooperative observing stations where people just measure daily Tmax and Tmin, but you need hourly data for your snow model. So you could fit geometric curves, like what's the typical sinusoid of diurnal temperature change over the day, and put that in. And then there's references for you if you need to look any of these up. Precipitation, often you only have daily precipitation totals for most places. So what are you going to do with that if you want it hourly? The most common is to just assume it's uniform every hour of the day. It's kind of a drizzle method, but it works better than anything else I've tried so far, short of using a full mesoscale model. Wind speed is very tricky. Most anemometers die in the snow. So typically you would interpolate from reanalysis data or from some other weather model. There's really a lack of robust methods to even empirically estimate wind speed. So going to atmospheric modeling communities, your best bet. If you want relative humidity, a common thing to do is assume that the minimum temperature each day is equal to the dew point temperature, and then you can calculate the relative humidity from the vapor pressure. And there's some references on that. Shortwave, I just went through, you calculate the transmissivity from the daily temperature range. This was investigated by a paper by Ted Bone. And then long wave, which is what you'll be doing for your homework 1. You empirically calculate what long wave should be from clear skies. It's a function of temperature and humidity. Basically, your primary emitter of long wave radiation in the atmosphere is the amount of moisture in the atmosphere. So you look at your relative humidity and estimate your long wave, and then you make an adjustment if you think there are clouds. This is what you'll be looking at. Any questions on that? Okay. All right, so now we can get all our data at a point. So what do we do if we want to move to places without weather stations? Ideas?
Interpolate?
Interpolate? Just spatially interpolate, least squares distance. What else should we think about?
Factor in topography and slope and aspect.
Absolutely, absolutely. So here's this again, here, don't worry about taking notes, but this is just a reference for you. This is published as, this is a PDF on the Canvas site too, if you don't want to have to look through this recording to find it. So if you want to distribute forcing, you could take output from any numerical weather model, right? It's going to give you a lot more points than your surface stations. You could use satellite data. You could use a gridded product where someone else did the interpolation for you. So an example might be the NLDAS data set or a hydroclimate forcing data set, such as there were a number developed for running the VIC model. There's a DayMet distributed data set. You could also use your local station data and knowledge of the terrain. This is what you guys were suggesting, to take into account, what's your slope aspect, shading, what are typical lapse rates in the area, and some software that does that that you can check out here includes Prism, TopoRad, MountainMet. A lot of these, if you want to run a fine resolution snow model, are still going to be required just to downscale any of the top choices you might choose. So here's just an example. This is where you might get some satellite data if you want from NSIDC. Again, it's mainly here for your reference. And then here are just some rules of thumb. If you have a weather station you want to distribute things, it's also worth knowing if you're looking at anybody else's output from their model and you want to know, like, why did they, they're running the same model as me and they came up with totally different snow than I did, what's going on? A lot of times there's a lot of subjectivity to these decisions, and you want to go check what is that person doing to distribute their met data and how might it affect their results. So for air temperature, it'll often, for complex terrain, be distributed with a lapse rate. The standard lapse rate for the entire world is -6.5 degrees Celsius per kilometer. Lack of anything else to do, that's a good number to grab. However, the standard lapse rate is often not a best choice. It's particularly bad in the Pacific Northwest, so you don't want to use it if you live in Washington. You might instead want to look at soundings, someone sending a balloon up with elevation, or Prism or WRF output. Precipitation, you need some spatial patterns. Where does it fall the most? Using spatial patterns fit, again, interpolation to multiple stations. Precipitation doesn't usually follow a lapse rate with elevation, so it's not as simple as temperature. Prism, which stands for Parameter Regression Infinite Slopes Model, thinks about slope and aspect and where you are relative to the coastline, is pretty good. There are some issues with storms that don't follow the climatology. It's climatology-based distribution method. For wind, same as before, you might want to downscale the wind with another model that considers topography and influences of topography on wind and snow. We're not going to get into that in this class, but I want you to be aware of, again, the references of what's out there. Most people assume relative humidity is constant with elevation. So temperature changes with elevation. And so the dew point temperature changes, but relative humidity, which is the percent of saturation, stays the same. A paper by Feld et al. Examined multiple methods for relative humidity. Mountains near coasts are particularly tricky because they're generally moister on one side and drier on the other. So think about proximity to coastline if you're worried about humidity. Right. Shortwave, adjust for topographic slope aspect. Shading from surrounding terrain, adjust for clouds. And finally, long wave, you adjust for elevation. Basically, there's less atmosphere above you at higher elevations, so there's less water vapor to emit long waves, so you have less long wave at higher elevations. You want to adjust for a sky view factor. How much of the sky do you see as opposed to mountains or trees or something else? Basically, long wave occurs over hemisphere. And the rule of thumb is a decrease in long wave of 30 watts per meter squared per kilometer. I know that's a lot of information really fast, and it's mostly because I want you to have it for reference. I see people are kind of nodding off. Any questions? All right. Okay, so here's a few examples. Let's go back to pictures. So here is just an example of how you might use, data at 6 kilometers as input to 150 meter resolution snow model. You could just do inverse distance weighting between locations. And then for precipitation, you could just do location. For temperature, which has a known elevation dependence, you could adjust for the altitude difference between your mean 6 kilometer elevation and 150 meter elevation. So you can interpolate with a linear offset based on the elevation. And then here's just some examples of things you might want to consider for figuring out solar radiation in complex terrain with lots of angles. Again, we're not going to get into the details of it for this class. We don't have time, but I just want people to have the references going forward if you're working in complex terrain with solar radiation. All right. All right, now, hold on just a second. I'll make sure it's not right. Okay, this is my son's school, so hold on just a second. Hello?
This conference will now be recorded.
Resume recording. All right. Okay, so now we are going to jump to, all right, I've got my forcing data. I figured out decent forcing data. Now I've got to run this particular model for this class, right? I've got to turn it on. I've got to run it. What do I do next? So SUMA, which is the model we're using, it reads in NetCDF files for the meteorology. For the purposes of this class, you do not need to know anything about a NetCDF file, so don't worry if that looks odd. If you start using it beyond this, then you'll need to learn. Details, we have all the meteorological files prepared for you, and you'll just be modifying them. The link for learning more about how SUMA is set up and the input and the MET forcing files is provided right here. And the things that each forcing file has are the same things that I just talked about for ideal weather station. One we didn't talk about is air pressure. The air pressure at the model forcing height in pascals. This is mainly to do a lot of calculations about vapor pressure. If you don't have a measurement of air pressure, you can just figure out the average air pressure at your elevation. So for sea level, it's 10, 13 millibars. Except it wants it in pascals and millibars. It's hectopascals for that, so you can convert it to pascals. All right. Okay. First thing, units. I think that somebody already mentioned what's the #1 thing you can do wrong in hydrology. Yeah, wrong units are the bane of everyone's existence. Hydrology is riddled with odd units. You will find weather stations that measure some things in metrics and other things in English and everything in between. You want to check both the data you're downloading and what your model expects. So this is what the SUMA model expects. The other thing that you want to think about is when it's expecting things at the model forcing height. So which of these things here, so that's basically when we have our weather tower, how high above the ground did we put our given instrument? Does that make sense? Versus how high does the model think we put our given instrument? So for which of these MET values do you think the forcing height is going to be most important to think about? What might change with height just above the ground?
Wind?
Wind, that's right.
Slow.
Hello? I heard wind and then something else. Chris is just laughing. I don't know.
Yeah, I was trying to say wind and then couldn't figure out the unmute thing.
Okay. Yeah, so wind, it has this logarithmic profile, right? But right next to the surface, it's not very windy. If you get up higher and higher above the surface, you expect the winds to be higher. And so the model will be scaling the winds from whatever height you give it to the expected winds at the surface. And if it doesn't have the right height, it can do some crazy things. So part of homework 1, not the one you'll turn in, but part 1C, will talk about the model forcing height and the winds, and you'll see what that does. Speaking of that height, the measurement height above bare ground, these you define not in your forcing file, but in what's called a local attributes file. It's also in NetCDF, and here's where you can look at it in the documentation for SUMA, and we will talk you through how to look at that. So here, so as looking at this, look at the PySUMA how-to document as well as homework 1. These are designed to let you know what are the different knobs and things you can get set up, how to find out what's in them. We have everything ready to go. We want you to be able to look at it and open it. So just for an example, when you're doing homework 1, and we'll talk on Wednesday more about the exact site where the data comes from, and once we start talking about forests. It has what's labeled as an HRU. So an HRU is a hydrologic response unit. And so you might say, okay, well, which is which and what's going on in this model? So how can we figure out what it is? So if you try typing in Python print best local attributes, this is what it gives me. It tells you, okay, this is the spot, and this is for the homework 1. You have 2 global response units and 2 hydrologic response units. And then I can tell you, just to save your time, you can look at any one of these. These differ by their vegetation type index and their measurement height. So you say, okay, well, so first you type this, it gives you the list of all the names. Then you say, I want to know this information about this specific name. So you can do print local attributes and name what you want to see the attributes of. And I get the first one that says, okay, but an HRU of 2, and the first is an array of 7 and 13, and that defines vegetation type, and then say, okay, 7 and 13 mean nothing to me, right? So up here at the top, veg type 7 and 13, you can look on the documentation on SUMA. SUMA tells you we got everything from NOAA MP. You then look up the documentation for NOAA MP, and if you go to this link and click on the vegetation parameters, you can learn that 7 is grassland and 13 is evergreen broadleaf forest. There's also evergreen needle-leaf forest. And if you're curious, I will let you go to NOAA MP and figure out what is the difference between a broadleaf versus a needle-leaf evergreen forest. But this is how you can figure out what that is. And then you can see that the measurement height is set at 3 and 15. Its long name is measurement height above bare ground, and its units are meter. So one thing that's important to know is if you set something up as having a forest, your model expects you to be measuring things on a tower above the forest. So you need to set a measurement height taller than whatever you tell it the height of the trees is. Now, you may not really be doing that, right? You could actually be measuring on the forest floor somewhere else, or something else, but you want to tell the model that you have a measurement at the top of the trees. So so here we have 2, and the measurement height the model is expecting is 3 meters and 15 meters. What might we want to change between the forcing data for these 2 response units? They're right next to each other. One's forest, one's grassland, or just an opening in the forest that we called grassland. So what do people think we might need to change? Can we use the same metadata for both of them?
Sorry, can you repeat the question?
Yes. So we and maybe this is just something to think about, and we'll revisit it on Wednesday. Is that so? We have that the model is we've got 2 sites right next to each other where we're modeling snow. One is snow under a tree, one is snow in an opening. We've told the model that we're measuring snow at 3 meters height over the opening where the grassland is, and at 15 meters height over the forest, because we're required to tell the model that we have a measurement above the top of the forest. In reality, I'm going to show you pictures from the site on Wednesday. We only have a measurement in the clearing. We just have 1 Met tower, maybe 2 or 3 meters in the clearing. Presuming it's a good Met tower, it's not blocked by any trees and shadiness, so it's open enough. Top of the canopy is not going to have any radiation blocked by trees, so above the canopy should be open. What might we need to adjust or change in our Met data?
So sorry, can I ask, does the 15 meters mean that your forest is 12 meters tall?
I didn't know.
3 meters above?
You have to go back to NOAA MP and find out how tall it thinks your evergreen forest is. It's probably, my forest is less than 15 meters. It's probably like 12 meters tall. And we could look that up.
But that 15 is saying that your measurement is 15 meters above.
So the model thinks my measurement is 15 meters above. My measurement really isn't.
And is it assuming, I guess, question of clarification, is it then assuming that the measurement would be taken either in an area that is broadly forest and really high up, or like in grassland? And I guess follow-up question is, what about the areas that are in between or are transitional?
So it doesn't like in between or transitional. It thinks that you are measuring high enough above the forest, but the forest is not impacting your measurement. So the model will adjust meteorology to the characteristics of the forest. It wants you to give it meteorology that is not influenced by the forest. Right, we'll come back to this. If you're curious, start playing with homework 1C, and you'll start seeing, and we can discuss more next time. And after you play with it, tell me if the answer makes sense. If it doesn't, we'll definitely work on it some more. You'll see quite a bit in this homework 1 talking about pointers of where your forcing files are. So we're going to be changing the forcing data, and we have to make sure we keep track of which forcing data goes with which model output. This is your most likely cause of problems, is you mislabel something or overwrite the wrong file. So here's just some directions of what this is, but the labs will, the lab and the homework Python files, you go through them and it'll talk about it. Just realize it's probably the most common problem. So even though it seems a little nitty-gritty, be very cognizant of what you're naming where. So just to summarize the getting data ready, the first thing is that all the data you need for this class are already up there. So if you're feeling overwhelmed, you don't need to. I'm going through this because I want people to be able to go run their own favorite site in the future if they want to. If you develop great pre-processing code for SUMA, please share it. It's basically PySUMA. So basically the model SUMA is run in Fortran. PySUMA is a Python wrapper to make it easier to adjust everything in SUMA. It's still under development. We are using PySUMA in all our online notebooks. So this is what we are doing. The install SUMA model configurations file shows you a lot of sites with forcing data that you can use to run a snow model, and you can choose for your project to use any of this data. I strongly recommend, given the timeline, that you only pick from these data files for this class. You don't have time to prep your own data files. We will provide you information for a home install at the end of class if you want to do it afterwards. And just one more time to remember, always convert your units to units required by the model. I can't tell you how many times I've done this wrong and seen students do this wrong. Easy to do. Always fill in every missing value. You have to put something or the model will not run. And then just estimate values for any term you don't have. So here's a Wikipedia for just coming up with a number for atmospheric pressure. And it makes almost no difference if you have it be constant through time for atmospheric pressure. Hold on a second. This is my son calling me. I'm having trouble, so okay. Hello, and pause.
This conference will now be recorded.
All right, sorry again. He's okay. Everybody's still alive, and he says he apologizes. It must be very embarrassing, and he'll talk to me later. And hopefully everyone will. Chris is laughing. Chris has a kid, right? It's a good day. I taught another class where every class of the quarter, one or another of my kids came down with a fever, and they always came down precisely in the middle of lecturing. Murphy's Law. All right. Any questions about all the logistics of that? It was a whole lot really fast. All right. Ready to do a climate model simulation? This is one of the most favorite things to do with snow modeling, right? Is, okay, we're pretty sure it's going to be warmer in the future. What's it going to do to my snowpack in my neck of the woods? So, you could go through a lot of effort to downscale a GCM, but, what if you just want a baseline check with a just delta T, right? I just want to test what happens to my snowpack if I warm the world by 2 degrees Celsius. Okay, so I take my line of temperature in my model and I add 2. Here's a question, am I done or what have I missed? How many people, thumbs up, say, I'm done, I did +2, I'm good. Because nobody thinks that's enough. So somebody tell me what else I need to do.
So probably change precipitation.
Should change what? Precipitation? How?
Well, just more higher temperatures, more evaporation, more precipitation.
So precipitations actually depends where you are. And if you know something, so if you have GCM, if you have something to base on from where you are, you could change the precipitation. For most places, it's kind of a shotgun blast in terms of what people think precipitation will do. So for some specific areas, that's a good idea, but in general, it's not an everywhere all the time kind of thing. You could just say, I'm going to do a sensitivity test and make it higher or lower because, and I'll make it both ways, and that's fine. But you would be fine saying, I have no idea, and keep it the same.
It seems like maybe your humidity would change if you change the temperature.
So humidity, so if you change the temperature, your saturation vapor pressure changes. The total amount of water you can hold changes. Your relative humidity might or might not. So 70%, you calculate it as a function of temperature. Does that make sense? So if you have 70% relative humidity, 70% actually has more water at a warmer temperature and 70% has less water at a lower temperature. So you need to update your amount of water, but you don't absolutely have to update your relative humidity. Does that make sense? But you are going to have, you have more water vapor now. Yeah. What?
Radiation.
Radiation. Which one?
Shortwave.
So why?
Because the temperature is increasing. So
Does the sun doing something different?
no, I guess not.
But what about the other one?
Long wave.
Long wave, exactly. Yeah, that's the really big one. So long wave is a function of both the amount of water vapor in the atmosphere and the temperature of the atmosphere, right? So long wave actually, this is the whole basis of the entire greenhouse gas effect, right? If we don't change long wave, we're doing a really terrible terrible warming experiment. So the reason why I chose for the first homework, you're going to do empirical methods of evaluating long wave, is that if you're trying to make a future projection of just delta T, you're going to have to estimate what that delta T does to long wave as well. And that's probably your biggest thing. So here's here's Jessica's rule of thumb of things to consider for a delta T experiment. In terms of air temperature, I tend to just change it uniformly according to the experiment. Like if I want +2, just what's going to happen. I do uniformly just to keep it simple, right? It's a sensitivity test. I could spend a lot of time doing something fancy if I wanted to. Precipitation, again, in the keep it simple, I assume it's the same as the historic data set. If you have reason for it to be different or you want to do precip as well as temperature sensitivity tests, you absolutely can change it. But as a baseline, most places it's not very certain. Winds, there's no evidence winds will change with temperature, so you can leave that the same. Relative humidity, as Megan suggested, we know the atmospheric water content is a function of both relative humidity and temperature. So water content in the atmosphere will go up, but we can assume the relative amount for that temperature is about the same. There are some papers that say that warmer air holds more moisture and relative humidity also goes up, but at a baseline, that's that for the relative humidity itself, it's not completely determined, so that's not critical. Solar radiation, unless you think cloudiness is going to change at your location or that pollution is going to get worse, right? You suddenly have more smoke particles, probably can assume it's the same. And then remember, long wave radiation is a function of temperature to the fourth, right? So this is the really key one. So if you forget this, in a model that takes long wave as input, you're not getting what you want. Any questions on just basics? This again is for your project if you're interested in doing this for one of the sites. This is kind of the rule of thumb you'd follow. All right. People can see me, okay. Somehow accidentally hid all the webcams. Where'd they go? Webcams, come back. So webcams, okay. All right. All right, so last bit. So in our last bit, I just want to give you what I call like my rule of thumb. So basically, when I started doing snow science, I kept discovering more and more that the biggest thing that changes your model is actually the MET data. So I spent years of just investigating each MET parameter one after the other. And I wanted to just give you the take-home message of, what are things that you should consider as you're picking MET data going forward in your life with your modeling. Okay, this is just a very short crash course. in take-home messages of if I were to pick my data for my model starting tomorrow, what would I grab right now for any station? Remember when I said last time that each person who teaches you tells you about their own background, what they're doing. I'm working in the Western US mountains. I'm going to show you supporting evidence, but most of it's based on Western US mountains. If you're far from US mountains, different things may apply. Number one, the absolute most common source of snow model error is precipitation. In remote snowy regions, it's very, very hard to measure. Generally, a high resolution atmospheric model will do better than observations left alone in the woods. Basically, you saw what happened to the one weather station, happens to a lot of them, unless there's somebody nearby watching your precip gauge in a place with snow, it's likely to have some problems. And so weather models tend to do better. You could use either an atmospheric model, or you can download the PRISM dataset for temperature. Again, as I mentioned before, be careful what your dataset is using. Some are particularly wrong for certain areas, so check. And you can check against temperature sensors at a lot of elevations. You can check against balloon sounding of temperature. Ceres is a satellite instrument on MODIS, and it does a really good job at getting incoming shortwave and longwave radiation. Also, the mountain climb is a preprocessor to come up with radiation. It's based on Tmax minus Tmin, and it does a really decent job. Again, as I showed you from Yosemite, you can go horribly wrong with grabbing a MET station with a solar radiometer on it, again, if people aren't cleaning it. Note that if you're using something, Ceres is a really coarse resolution, it's about 2 degrees. For your incoming short and long wave radiation, you need to be sure that you adjust your long wave for elevation. Remember, there's less incoming long wave at higher elevation, and that you incorporate topographic shading for shortwave. The atmospheric model is good for precipitation. It is not very good for radiation. Basically, the atmospheric modelers have focused on their targets, which are basically precipitation forecasting. So they do really well at precipitation, and the radiation algorithms in atmospheric models are less well developed. Some of the stuff coming out from the solar energy community is getting really good, because their goal, right, is to forecast how much you'll get out of your solar panels you put out in different places. But right now, either just empirical method or Ceres is important. Relative humidity is less critical. If you just change it on your homework, you'll see it doesn't make a huge difference in most cases, but there is a paper you can see for an analysis. Wind is still a big problem. It's an ongoing source of more research, but right now my current recommendation would be go with the highest resolution mesoscale atmospheric model you could get, HER, which is run operationally in the US at about 3 kilometers resolution and archived at Utah, is a decent solution for wind, unique wind data. That was a lot. Any questions? Again, this is a reference, and you can download it and look it up again at some point if it proves useful. All right. So, so when you're thinking about, what are the signals of different data that you might pull in, and how is it going to show up in things you might care about? So right here this is what I like to think about as the phases of the snowpack and the stream flow. So for most places, we have an accumulation season where we can explain most of what's going on in the snowpack in terms of snow accumulation. We then have a season where we have snow sitting on the ground, and the snow is what's called getting ripening. So so this is, on the y-axis is snow depth, and going across, you see the colors are density. And so the really dark blue is really light density, and the green is a really high density. And so you can see that new snowfall is the lightest density, that as the snow settles, the layers get buried, and over time, the snowpack gets warmer, it metamorphoses, and it comes up with higher density. So you have a season where the snowpack is dominated primarily by energy balance and snow temperature. It's not doing a whole lot for a while. I mean, there might be another big storm, but it's just waiting to start melting. And then you have a season where the snow is rapidly melting and disappearing different places in your domain. And you can see that here, it's basically at the end of this energy balance is when the stream flow starts going up. Stream flow will stay high as long as there's lots of snow in your basin. And if you have a snow dominated basin, when the snow's gone, right, stream flow is going to start going away. Stream flow drops as the snow disappears. So how can we use this to understand what we should look at in our modeling decisions? So one metric is that the snow accumulation, right? The total amount of snow you get. If you're in a snow-dominated basin, which I've drawn here, and this really determines the total volume of the runoff you're getting from the snow, right? But the amount of water is probably something less than this amount that accumulated, right? Presuming you've got snow and not a lot of rain. And so this is probably for most water resources our number one thing, right? The snow surveys go out and they try to measure peak snow at peak accumulation to give a forecast of how much water will we have downstream in the spring. So how are we doing at this? So this is from a paper Mark Rowley put together where he's really asking what forcing data matters most to model the snow. And he tried to grab sites in very different climates. These are snow classes put together. In Naviet Creek, right here, that's the first one I showed you. That's the one up in Alaska that got all the snow drifts. Reynolds Mountain East is in Idaho. Senator Beck, SP, forget, this is in Colorado, in Senator Beck Basin, and then Col de Port is in France, is a more maritime site. So the first thing you can see is, so this is running the black lines here. So you can see these are those 4 sites. The black lines here are observations. You can see at this Alaska site that we started trapping snow behind the wind drift right here. So the observations show a lot of snow that might not be representative of what's around it. The other ones I think are all pretty representative. And so the black line is the observations. The red line is a model if we use all observations that are available at the site. The blue line is what we get if we just empirically estimate all the observations. We presume that they're not available. And then the gray traces are all model simulations with all different combinations of estimating 1, 2, or 3 observations. Just different ways you can estimate things. So what do we see here? So the first thing is that at the warmer sites, if you measure precipitation, you get snowfall right, and you actually observe it, you come pretty close to accumulating the right amount of snow. At the colder sites with lighter snow that blows around, you can see that the undercatch and redistribution are actually problematic, right? We don't, even using all the observations we have at our site, we don't actually model the snow, observe snow accumulation very well, right? All the simulations are off because the metadata is off. Again, here's this picture again, which you came in a little bit late. You missed our snowdrift alter shield fence. Okay, at most sites, if we got the accumulation right, we can model melt pretty well, right? These slopes of going down how fast the snow is melting, it is, for most sites, not this one, but for these 3, they're all pretty well with all different forcing data we can do. So the other thing to note is if you think about, you'll see, one thing you see is where they all start diverging right here. Can you guys see my pointer? Yes. So you can see that it's right here where melt starts. They all kind of agree on the melt, and when melt starts is when they have problems. So this is when you actually want to worry about your midwinter energy balance. And we'll be really looking at this in the second homework and in modeling, how we modeled this right with our model. So our evolution of snow temperature determines whether and when midwinter melt will occur. And this determines the onset of stream flow, or if you're going to have a flood from warming in the spring, when it's going to happen. So this is just another picture looking at all the components we've just been going through of the energy balance over the snowpack and all the different terms. And again, most snow models are based in well-known physics and perform fairly well given accurate forcing data. However, the surface energy balance can be hard to come by in remote regions. And you can see here that I've got arrows, what I was circling before, is that the greatest divergence besides the issues with just getting precipitation right is when the melt turns on here, right? You've got the very wide variety at the Colorado Alpine site. You can actually track this. You can track this with the surface temperature. So this is a picture at Snoqualmie Pass. This is is output from the SUMA model, which you'll all be using. And looking at this, so Snoqualmie is a maritime site, it rains on it. Orange here is 0. So when the snow is cold, so here you see these are some cold nights, the snow is getting really cold. It's not ready to melt, it's still cold. And here in the orange is when the snow is isothermal at 0, ready to melt. Once you've warmed the snow up to 0, that's when you get this rapid snow melt and disappearance. So this is where we're going to be going with this next week, into more about the surface temperature and how that reflects the energy balance as well as the internal states of our snow model. Okay. So Mark Rowley, after his study, he concluded that precipitation was by far the most important. Long wave radiation came in second. So that's another reason why to play with that with your homework this week. And short wave radiation came in third. So given precipitation is so critical to snow modeling, a lot of people get uncomfortable, and I recommend they use model output over observations for precipitation. Anybody feeling that way? I feel like I've just been talking too long and I should stop. Sometimes I get tired. What do you guys think? Given what I've showed you so far, given precipitation is critically important, more than anything else, is it safe to have one model trust another model? What should we be doing here? Any thoughts?
I feel like it just depends. Like it depends on like the data available / the scale that you're looking at. Maybe because I feel like the caution I feel of using model data in a model is then you might be kind of building some uncertainties and on uncertainties. But if there isn't anything available, perhaps that's a better option. But if there is something available or other data sets, it might be something worth going down. I don't know.
Yeah, it's a really tricky issue, right? You can imagine like the Arctic site, probably the atmospheric models are pretty bad up there too, right? But the observations sitting there are also quite problematic. You have thoughts what you would do if you were up at that site?
What about averaging your model and your observations?
Yeah, you could do some weighted averaging. You could do some kind of how much you trust all the different sources for input. what they honestly do up in Alaska is they actually go and do surveys of the snow in the middle of the winter, and you could then initialize your model or update your model with a measure of snow. You could say I got precip wrong, I measured snow at some point, and I'm going to update snow to give me the right depth. And then I'm pretty good at modeling the melt. If I've got the right depth, I have one measurement to update my depth at some point in time. So you can kind of give up, but measuring the snowfall state whatsoever is one approach. We're not trying to do it in the class, but I just want people to be aware of it. So this is just one reason. One reason why it's just so problematic. These are pictures from a review of snowfall measurements worldwide that was put out in the Bulletin of American Meteorological Society by Roy Rasmussen in 2011. And he had 1, 2, 3, 4, about 7 or 8 snowfall gauges set out right next to each other in Boulder, Colorado. And this was, basically their difference, and they were all sitting right next to each other. So they differed by a factor of 2 just by which type you put there. So it's just hard to do. And so it's just a very important thing to be cognizant of, in that how important it is to get the right input data, particularly the amount of snow you put into your system for your snow model, or it doesn't matter how brilliant a snow modeler you are, you won't come out of it. I am going to, in the interest of time, I'm just going to skip ahead here. You have this if you're interested in looking at it. Those were some details about different precip data sets, but I feel like I've gone over a lot today, so I don't want to go into that. The other thing I want to mention is cases that occur all the time in my backyard that are likely to occur more frequently in other people's backyard is rain versus snow, or what Seattleites like to call the wintry mix, where you get rain and snow all at once, and then the road freezing and shut down the whole city. There's a nice paper by Keith Jennings that came out recently that looked at all kinds of different empirical methods people use to figure out rain versus snow. It turns out that most of them are really quite bad, and I would like to recommend, in addition to precipitation, that you consider atmospheric models actually do better at separating rain from snow. So as another input, what we typically do is we say, okay, we have precip, right, that we measured somewhere in a bucket. We just do temperature, and we say the temperature is, below 0, it's snow. If the temperature is above 0, it's rain. In reality, there actually are hydrometeors falling through the atmosphere, which has lots of different temperatures, right? And the plus of an atmospheric model is it's actually tracking where that hydrometeor was before it got to the surface. So if you have, you may have, very fast falling heavy snowflakes that will still last and fall at surface even at 3 degrees Celsius, because they are cold and you're not overcoming the snowflakes cold content. They don't have time to melt. So this is just a picture from a paper by William Currier. We were looking on the Olympics. There's also a paper by Nick Land in the Cascades. In both cases, where we had just tons of wintry mixed precipitation, using WRF's microphysics scheme, which actually tracks your amount of frozen versus solid particles falling through the atmosphere, gave a better partitioning of rain versus snow than anything we could do based on temperature or relative humidity. So that's a recommendation. This is just details of Snoqualmie Pass site, which I'm going to skip. And then if you just want a literature review of lots of literature that talks about whether or not you might want modeled versus observed precipitation, this has lots of literature in it. I stuck it in your folder. If you're curious, if you're not, it's not required reading, so you don't need to look at it. All right, so we've got a few minutes left. That's all the material I want to show you today. Any questions about anything? I'm guessing the best is to just start turning on the model, pushing buttons, seeing if you can make things work, and send me questions as they come up, okay? All right, thank you. You've got questions? Yeah.
It's not as much of a question, but on the what's it called, the Canvas page, the hydro.pangeo.io, I wasn't having that link work, but when I just typed it in separately, it did work. So I don't know if maybe it's just my browser, but
it could be there's something wrong with the link. Let's see. It's in Canvas.
Yeah, under homework 1, I just wasn't having the hydro.pangeo.io, the second link. Yeah.
Yeah.
But maybe if I, oh yeah, okay.
So just type it in. Don't click on that link.
Yeah. If you type it, it works.
Yeah. So clearly you can see it didn't work on mine either. I think I just mistyped the link. So I will type the link. Mm-hmm. And then I see a couple comments. Sarah's asking, is it because modeled output more accurate than sparse observational data? That's true, right? A model generally will fill in the details better than interpolation when we have very limited measurements. And then Camilla said latent heat should be updated, and I'm not sure what that means. So maybe Camilla can follow up with, I'm guessing there was a typo in one of my slides. You can help me out, I'll update that one.
I think that was in reference to what to do about testing the 2-degree increase in temperature.
Oh, yeah, you're absolutely right. Latent heat should be updated as well. It's actually calculated by the model, so you don't have to change it in the forcing files. Does that make sense? That'll be the model's job, is to update the latent heat flags.
I just had a really simple question, but what time zone is Canvas in?
I do not know, but if you're within any range of US time zones of the due date, I'll forgive you. Does that make sense?
Yeah, great.
Calculate you're within.
Yeah.
The class starts, and Canvas is probably at East Coast time. So if it gives you a timestamp, so it told you were late, don't worry about it.
Okay, thank you.
You're welcome. So that's a very good question, and I can set the due date later because clearly I'm on West Coast time. Mm-hmm. I'll send it later in the day. Anything else? All right. I will see you all again on Wednesday, and I'll watch my inbox if anything comes up before then. Do try to look at the programming homework so you can ask questions on Wednesday. All right. Thank you.
Thanks, Jessica.
Thank you.
Thank you.
Thank you.
Thank you.